Hi, good afternoon. This video is to introduce the material related to thermal properties of matter. Then we are going to introduce in this chapter, in this video, thermal properties of matter. And here we need to differentiate between two point of views. One of them we call it macroscopic, which is like about kind of bulk view, which here we focus on I will say large scale variables. Large scale variables are like volume, P for pressure, T for temperature, and R all related. Now microscopic point of view, it is talking about small scale variables. And here we are digging inside the material to talk about speeds, kinetic energy, energies, momenta, and other related topics. And I will say here, the first thing that we are going to introduce, it is the concept of the mole and Avogadro's number. And maybe if you took a chemistry class before, you are familiar with these. Now, 1 mole of any pure element or compound contains a definite number of molecules. This is very similar to make it like closer to you, a dozen. A dozen from any material or from anything is going to be 12. Here again, it's the same thing. Any mole of any substance is going to have a definite number of molecules. That definite numbers, we call it Avogadro's number. And that Avogadro's number, it has this notation Na, and it is 6.022 10 to 23 molecule, or like, atom per mole. Then if I have any mole of, let's say, an element or a compound, is going to be having this number of molecules, or I will say atoms. Now also we need here maybe to talk more about more things like the molar mass. And the molar mass, it is, we give it like uppercase M, and that is the mass of 1 mole. And then when you are going to view the periodic table, you're going to find these, atomic, I would say, molar masses listed. Also, here I will say there is a relation between M and M. Now, lowercase m, it is the mass of one molecule or atom. I can say also that the mass, the total mass, and what does it mean, the total mass? The total mass of a substance N equals N times the molar mass. And here it is the number of moles. And again, uppercase M, it is the mass per mole, which is, we did say, it is the molar mass. Now, one of the things that maybe we are going to introduce also here, it is something that you did learn maybe in chemistry, and the name that we are using for it usually, it is the ideal gas equation, or another name which is maybe, let's say, more fancy, it is the equation of state. Now, the equation of state here, we are talking about, I would say, large-scale variables. And I will say here, we need to do some of kind, I would say, conclusions here. About the gas or gases. And these are when the gas is at low pressure. The volume V is proportional to the number of moles N. The number of moles N. And also it has to do with the number of molecules. And I think this is making sense. More molecules, you're gonna have more volume. Now, I will say then, if the number of moles is doubled, then the pressure, the volume doubles. But of course, this is keeping pressure and temperature constant. Now, the second important conclusion, it is the volume And this is something that, again, very, I will say, famous, Boyle's law. The volume varies inversely with the pressure P. And then here, if I will have, PV always equal a constant, which means if you double the pressure, and then we're gonna find that the volume is gonna decrease to 1/2. Now also, the third important conclusion from experiments is that the pressure itself is directly proportional to the absolute or Kelvin temperature. Now, then we can say, having all these conclusions together, that the equation of state, or the ideal gas equation, is gonna be written as P times V equals nRT. What are these variables? First, P, it is pressure, and I'm gonna talk about the ideal units when I have pressure in pascals. V, it is volume, and here it is in cubic meters. N, it is number of moles, and T, it should be temperature in kelvins. Now R here, it is a constant, and of course this constant is depending on the unit. Then if I have the units here as stated before, this is gonna be 8.3145 joule per mole Kelvin. Now there is another way of, like, another set of units that we are using, and that when we have pressure in atmospheres, and when I have volume in liters, now R is gonna be another value, which is 0.08206 liter per atmosphere divided by mole Kelvin. Then it depends, as I said, value of R depends on what are really the values that I'm using for the volume and the pressure. Now also here we can get an expression from this to calculate density. Remember, density, it is mass per unit volume. Then rho, it is mass, let's say total, divided by volume. And that rho equals the pressure times M, the molar mass, divided by RT. This is one of the equations that we are using for density. And also, I would say here, we can actually, whenever we can have, when constant mass, which means constant number of molecules or atoms, we can say that P1 V1 over T1 should equals P2 times V2 over T2, and that is really, it should be a constant. Let me solve this problem for you, and that is something that is going to be very basic. What is the volume of a gas at STP? Okay, STP stands for standard temperature and pressure. Now that means that the temperature is going to be 0 Celsius, which is 273 Kelvin, and the pressure is 1 atmosphere, which is 1.013 10 to the 5 pascals. And I will say now we are going to find, we want to find the volume of 1 mole of helium gas in a room at STP. Okay, now of course we know that this is BV equals nRT, and the volume is going to be nRT over P. By the way, P always should be like a lowercase for pressure. And that is gonna be 1 mole. T here, we are using the standard units. Divided by 1.013 times 10 to the 5 pascals, and of course T here, which is the 27, and that is going to be 0.0224 cubic meters, which is 22.4 liter. And actually this is really for any gas, okay, that can be considered ideal at STP. Okay, I'm gonna stop here for this chapter and see you in another video.